Example 2. Let's see if Q represent the cost, R of Q represent the revenue, and pi of Q represent the profit of a product with quantity Q. Part A. When profit is maximized, what is the relationship between the derivative of cost and the derivative of revenue? So let's review what we know about the profit function. Really, we don't know too much, but we do know that profit is revenue minus cost. Now, with revenue minus cost, we don't have the derivatives in there yet. And so we're trying to think about what this has to do with the question being asked. So the other important part of this problem is the part of the question that asks when the profit is maximized. So remember, when we want to look for a maximum, we're interested in where the first derivative equals 0. We know that if we have a maximum, that the first derivative of profit will equal 0. Well, what do we know about the first derivative of profit? So here, marginal profit, we have two terms, revenue and cost, that are separated by subtraction. When we take derivatives, if things are separated by addition or subtraction, we can take the derivative term by term, which means we can write the derivative of revenue as R prime of Q, or marginal revenue. And then we can write the cost derivative as C prime of Q. Now, if we're at a maximum, that means we're at a critical point. So the difference between these two things will have to be 0. Well, that tells me something really important, because if I were to add C prime of Q over to the right, I will find that R prime of Q equals C prime of Q. So that tells me that when profit is maximized, the marginal revenue has to be equal to the marginal cost. This is a little tidbit that comes in handy in strange ways, but it's something that's useful in a lot of ways. If our marginal revenue equals our marginal cost, we have the right condition for the profit to be maximized. Part B. If the marginal revenue of cost at 45 items is $57 per item, and the marginal revenue at 45 items is $62 per item, approximately how much additional profit is earned by the 46th item? Now, we have to be a little careful here, and our analysis is the 1 unit marginal analysis that we were doing when we were talking about derivatives before. So I want you to notice that the information we have is about what's happening when Q equals 45. So if we're talking about the additional profit earned by the 46th item, then we're looking for the amount of profit that we get from moving from 45 to 46 items. Remember, when we talk about derivatives, we're talking about increasing the independent variable by 1 unit and looking at what the change is in the dependent variable. Here, that dependent variable is profit. So we're looking at what happens as we move from 45 items to 46 items. And so again, the additional profit is the marginal profit. So that's the rate at which the profit is changing. So we want to talk about marginal profit at 45 items, because that's going to tell me how much additional profit I make to go from 45 to 46, and therefore identifies the additional profit earned by the 46th item. Well, as we saw in the previous part of this example, we know that marginal profit is marginal revenue minus marginal cost. But we're looking at all of these things for Q equals 45. So we need the marginal revenue at 45 minus the marginal cost at 45. So we know these values from the earlier part of the problem. It's going to be $62 per item minus $57 per item, which tells me that the marginal profit is $5 per item. So that tells me that if I were to go from making and selling 45 items to making and selling 46 items, I will receive an additional $5 in profit. Let's look at one more example. Example 3. A theater has 1,000 seats, and when they set their ticket price at $10 per ticket, the theater sells out. So they sell all 1,000 tickets. For each additional dollar charged, the number of seats purchased is reduced by 50. Part A. Find the linear equation that fits this data. Instead of using the variables x and y, substitute q and p into your equation. This is what we call the demand equation. The demand equation relates how many tickets will be demanded depending on the price that you're picking. So we want to have a relationship with q and p. So it doesn't matter which way we set this up as long as we're careful and we're consistent. So how do we do this? So we want to write these informational points, 1,000 seats, $10, as points as though we were plotting them on a graph. So the first point would be 1,010. Now, the second point that we have from information from this problem here is that if we charge an additional dollar, so that means instead of 10, we're going to have 11, the number of seats purchased is reduced by 50. So we're going to subtract 50 from 1,000, and that'll give me 950. So these are two data points. And normally, I write my points x, y. But I want you to notice here that what I'm talking about is quantity, price. So what I'm going to do is I'm going to come up with a linear equation that fits this data using y equals mx plus b. Once I have the equation of that line, I'm going to change my x and my y into q and p so that I have a demand equation. So let's find the slope that's going to fit between these lines. So remember, slope is change in y over change in x. So here, I'm going to do 11 minus 10 divided by 950 minus 1,000. That's going to give me negative 1 over 50. So the slope of my line is negative 1/50th. So here I have y equals negative 1/50th x plus b. In order to solve for b, I need to plug in one of my points. It doesn't matter which point I plug in, I'll get the same answer. So I'm going to use the first one. So for my first one, if I plug in my point, I have 10 equals negative 1/50th times 1,000 plus b. Negative 1/50th times 1,000 gives me negative 20. If I add that over to the left, I get b equals 30. Which means the equation of my line is y equals negative 1/50th x plus 30. Now remember, we don't want our answer in x's and y's. We want it in q's and p's. So we go back to our original setup, and again, we had q, p. Quantity, price, which means that instead of x, I'm going to write q, and instead of y, I'm going to write p. So I have p equals negative 150q plus 30. So this is my demand equation. And again, a demand equation relates price and quantity. So you, as the producer, can figure out the right balance. We could solve for Q if we wanted to and then vary the price, or we, in this case, are varying Q and using that to set the price. Now, remember from before that revenue is price times quantity. Part B. Using your equation from part A, set up the revenue equation by substituting the demand equation in for P. So what does that mean? So remember, revenue is price times quantity. What this is saying is that instead of P, we're going to use what we just found for P setting up our demand equation. So that's going to give me negative 1/50th Q plus 30 times Q. Now I can distribute that Q through and simplify a little. So I'll get negative 1/50th Q squared plus 30Q. So that's my revenue equation for this particular model. And again, I got this set up by plugging my demand equation in for P and then distributing the Q. So now for part C, I want to find the price and quantity that will maximize revenue. Well, all the work I was doing before was to get my revenue equation set up. Now that my revenue equation is all set up, I can maximize it by using derivatives. So again, I want to find where the first derivative of this function equals 0, because then I will have a critical point, and I know that maximums happen at critical points. So let's see what the first derivative looks like. So here, the first derivative of revenue, we go to the first term. I have negative 1/50th q squared, so the 2 comes down. I have negative 2/50ths q to the 1 power, plus the derivative of 30q is 30. And I want to know, when does that equal 0? So now I can take my q term and bring it over to the right, and I will get 30 equals 2/50ths q. Now I'm going to multiply by the reciprocal of that fraction to get it out of there. So multiplying both sides by 50 over 2 is going to give me that q equals 750. So now I have my critical point. If I were to take the second derivative of this function, I would have negative 2/50ths, which tells me that my revenue equation is concave down everywhere. Since it's concave down everywhere, I know that my q has to be a maximum. So that's the quantity that maximizes my revenue here. I also want to know the price. So in order to find the corresponding price, I have to go back to my demand equation, which is way up here in part A, and I need to substitute my q in. So I have negative 1/50th times 750 plus 30. If I crunch that number, I'm going to get P equals 15. So price is going to be in dollars. So I could figure out what my revenue would be here by multiplying P times Q, but that's not what the question asked. So I'm able to find all sorts of things if I carefully set up my equations and use the calculus that I've learned to evaluate them.